In the second set of problems, we look at the sum of two IID uniform random variables. We'll solve this problem in two methods. The first one is by convolution, which is what you see on this slide. And in the next one, we are going to solve by transformation of variables. So x1 and x2 are two uniform random variables, independent and identically distributed between 0 and 1. So we want to find the distribution of their sum. So let's start with the basic definition of the CDF of y, which is the sum of x1 and x2. And we just write it as the double integration over x1 and x2 of the region in which the sum is less than little y, for which we have used the indicator function, as you see. So now we can differentiate this to get the PDF of y. Let's do that. And when we differentiate the indicator function, we get the delta function. If we write it out in terms of x2, then we can get rid of the integration with respect to x2 and end up with a one-dimensional integration involving x1 only. Y is a parameter that's not dependent on x1. So now we make use of the fact that x1 and x2 are uniform, and fx1 and fx2 are defined only in the interval 0 and 1. So once we use that fact, we can simplify the density of y in terms of just one indicator function. So we are now integrating over all values of x1, but making sure that y minus x1 is positive on one end and less than 1 on the other. So now it's convenient to split this integration for two sets of values of y. So one in which y is between 0 and 1, and the other in which the y is between 1 and 2. So in the first range, the density of y simplifies to y itself, that's between 0 and 1. And in the second range, between 1 and 2, the density integrates to 2 minus y. So that's between 1 and 2. So putting these two things together, it's clear that the sum of two independent standard uniforms is the triangular random variable. So its density function is a triangle symmetric about the point 1. And in fact, this is kind of a precursor to what we will see later when we add several such uniforms. So if we added a few more uniforms, it's going to look more and more like the normal density function. And just by adding two of them, you kind of start getting the shape. Now we'll solve the same problem by transformation of variables, which we looked at a couple slides ago. So it's the same problem, but now we have x1 and x2 on one side and just y on the other side. So we need to introduce one sort of dummy variable, as we discussed. So to make the problem 2 by 2. So let y1 be x1 plus x2, and then we define a new variable y2, which is identical to x2. And now we need to invert that relation also. So x1 in terms of y1 and y2, and x2 in terms of y1 and y2. In this case only x2 is equal to y2. So this lets us write the Jacobian, and it's a constant equal to 1, and that lets us describe the joint density of y1 and y2 in terms of the joint density of x1 and x2, and we conveniently make use of the fact that x1 and x2 are independent, so the joint density is the product of the marginal densities. Once we do that, we should express the x1s and the x2 in terms of y1 and y2. So that gives us the joint density of y1 and y2 in terms of the product of two indicator functions, one involving y1 minus y2 and the other involving just y2. So the marginal density of y1, which is what we need, we can get it simply by integrating out y2 from the joint density function. So that's what we do, and now we just need to make sure that the indicator functions are properly accounted for. So the limits of the integration can be found to be, as I have written on the screen. So the lower limit is maximum of 0 and y1 minus 1, and the upper limit is minimum of y1 and 1. And if you complete the integration, then you get again two ranges of y1. The first one is 0 to 1, and the second one is 1 to 2, and you get the same triangular density function as before.